Piezo SHOCK Show. Let's talk about what the difference is between square and sine wave drive of ultrasonic transducers. This is a question kind of reappearing. They are both signals which oscillate. Therefore, they should be able to both drive ultrasonic transducers into oscillation at the right frequency. So let's take a look at some of the differences, and perhaps you kind of will understand through this discussion what you should choose for what application. Now, I'll preface this and just give you the lowdown, and if you can use sine, there is no reason to use square. If you can use sine waves, you will not, and you should not use square waves. Except in some applications, very rare, that you need multiple harmonics being driven. In that case, yeah. But even in that case, if you drive with multiple sine waves, it's still better than using square. Now, for some applications, it's not going to be as important. But for power ultrasonics, yes, it is. Like, you don't use square waves, you use sine waves. And whether you start with a square wave or not, that's another question. But what you want to reach your transducer would be a sine wave. But you can make practically good devices, simple topologies with squares. Let's talk about it, because that's why you're here. So this is a square wave. It has jagged edges. This is a sine wave. It has smooth edges. It doesn't have any kinks. Now, truly, in a square wave, there's this transition point between low and high. It's not infinitely fast. There is actually a finite time it's going to take. So just recognize that the square waves are never really perfect. They always come with their own imperfections. So the biggest difference between just looking at the waves themselves is the spectral content, which you can use using an FFT, for example. Plug in to your oscilloscope a square wave from a function generator, or even from the calibration pins that produces a 1 kilohertz wave, and then you implement the FFT and see the spectrum. I believe this is correct for a square wave. It's odd harmonics. So basically, the square wave contains a lot more frequencies than the sine wave, which has has minor frequency content in other regions, but that's just because the reality of using a real amplifier, a real signal generator, there are going to be imperfections. That's just part of it, but they're very small. They're insignificant, except when they are significant, which we could talk about that later. But in most cases, that's what we're discussing. It's not you have a practical pure sine wave, but you have these. But what's the harm in this? Okay, what's the harm in using a square wave for driving? So one of the first harms that you get from a square wave is that the amplitude of the square wave is not actually, if it was a pure sine wave at the same amplitude, you would actually have more apparent amplitude at that frequency. So you have to note that even if you have a square wave and a sine wave at the same amplitude, the sine wave is going to have a higher spectral content even for that driving mode, and obviously it will lack spectral content for the higher order modes, which can cause issues, and I'll describe those. So I also have another video that I talked about square and sine waves, so I'm going to link that in the description. It talks a little bit more about how square waves are actually consist of different frequencies. So I have a video on that. I'll put it in the description. But let's continue with the shock show version of it. Okay. So what happens if you have an impedance like this? We have multiple peaks, and you are driving at multiple you're driving using a square wave, driving at different frequencies. Let's say you're targeting this mode here, right? And you have, let's say, your other harmonic lands right there. These are actually not too different in impedance. This resonance and like this other off spot, they're not very different in impedance. So you'll actually have a huge contribution to your final wave. It's not just, I put in a square wave to my transducer and it rejects all other modes. Yes, it will reject all other modes, but electrically you're also stimulating a lot of current and at those frequencies due to capacitive behavior. So that is something to note too. And also the square wave just naturally stimulates other resonant modes which may have a very high quality factor, because there could be other modes lurking in the space that even though it's like, let's say the ninth mode or the fifth mode, but it's like just one metallic part of your transducer oscillating and it has a really high quality factor, that can also become a huge problem. So basically these extra modes, these extra frequencies stimulated, in some cases you can live with it. In some cases you can't live with it. You can't operate your device for several reasons, and I'll describe those. So let's just get into square and sine. Let's get a little bit of a bullet list going. So square wave, use a bridge driver. You turn on and off your connections through switches, and amplifiers are basically they are biased MOSFETs or BJTs, and there's a complex topology, but basically you do get input sine and out your output signal matches your input signal, but this also sort of hurts you in terms of the frequency response. Square waves are going to be much higher for frequency response. I'm not sure, but I believe ultrasonic, like high frequency drivers, for ultrasound diagnostic applications, I believe they use square waves. I haven't worked on those specifically, so I can't speak perfectly, but I think they use square waves, and always, and a good reason for that would be, well, you can hit high frequencies. And you can have a simple enough drive topology to drive multiple channels with ease. But for power ultrasonics, sub 1 kilohertz, 100 kilohertz, yeah, you're gonna benefit a lot from using a sine wave style driver if you can. And, if space and cost are less of a concern, you can, and also power to that amplifier, because they do have their inefficiencies. Then you may look into a square wave if that works for you, or a bridge driver. Next, if there's a transformer involved, because I mentioned there's a transformer, either a step up or step down voltage. For a square wave, you're putting a lot more electrical stuff inside of that transformer. You're more likely to saturate it than you would in a sinusoidal application. Now you can use filtering, so you can start with a square wave and end up with a sine wave. That happens all the time. But you may lack some of the amplitude resolution. Now there may be ways to get around it. I haven't seen it in practice, but obviously you can change DC voltage levels, although those are not the most convenient thing to change. You use an op amp for something like that. Back to the amplifier then. Okay, so you can saturate the transformer. The other thing about square waves is you can transform them into sine waves using LC networks. And also just designing your transducer. So sometimes you can also design your transducer such that it works better with the square wave circuit. So if you know that you're limited in your part count and your costs, or you already have an existing driver that's absolutely perfect, you think, you can do things to your transducer design to make it better for that driver. It just depends on where you want to put your constraints. Engineers need constraints for their projects. Here's one of them if you're lacking some. So the next part is that it's hard to do feedback with square waves because there are multiple frequencies involved. Now you can do filtering with that, but it doesn't. You can't just as easily pull the current. In some applications, you won't just be able to pull the current in order to do feedback to find the resonant frequency, and the phase will be a lot more blurry. It'll be hard to calculate power from single value measurements. So that could be more difficult with a sine wave. Obviously, your response should be a sine wave, where it's close enough that you can calculate phase and amplitude and get power and do calculations like that. The last one here I have one more, is there's extra excitation in the square wave. So we're putting energy in the system at not only the primary drive frequency, but also higher, odd harmonics, assuming it's a 50% duty cycle. And that energy can heat the device. It can also further stress your piezo. It can also highlight modes which will more readily cause failure. It can cause also noise and other unwanted effects. So that's what I have to say for extra excitation. Obviously, the sine wave is more pure for that. Another thing I want to mention is that if you have an anti-resonance drive, you're driving at the anti-resonance frequency, highest impedance. At that point, it becomes very important that your drive signal is pure, because if you drive, let's say you drive, you have a device and it only has one resonance somehow. So it has a resonance at 50 kilohertz, or anti-resonance at 50 kilohertz, and you're driving your transducer there for the reasons and the benefits that you get from anti-resonance. Load and sensitivity, voltage controlling amplitude, so that makes it a very consistent device. And so what happens there is that let's say your anti-resonance impedance is let's say 30 kilo ohms, let's say, and and when you actually stimulate your third harmonic is going to be at a lower impedance than that anti-resonance. So you're actually the current is going to be dominated by a third. Not only is it going to be like a little annoying, like superposition, it's going to be the main thing, and the superposition is going to be your anti-resonance. Now, if you somehow are able to still lock on to that frequency using other means and methods, then you can still drive it in those conditions. But it starts to become a little bit absurd that you are you're stimulating so much current and you're hardly getting anything from your actual drive. So yeah, if you do voltage times current, you'll get a power value that represents the power dissipated at that anti-resonance frequency, assuming that the off resonance point is not really oscillating too much. It's just mainly the capacitive style response. But you'll still end up in a kind of weird predicament with a lot of useless current, and that also causes heating. That's another kind of side benefit of anti-resonance, is there's lower flow of current, there's less heating, at least in the electrical connections, and there's less ohmic loss, which can be large, and it can also be mistaken for poor transducer. Ohmic loss can also lead to heating if the current is high enough and the wires and the connections are not high enough quality. So you have been watching your host, Dr. Shikani, answer your questions on ultrasonic transducers and piezoelectric devices. Check the links in the description for the video I mentioned. It gives you another video that I have for square versus sine wave drive. I also have, I'm going to put a link in the description to the presentation notes today. I also have a link to my consulting services for ultrasonic transducer development. Having an experienced transducer expert on your team will allow your projects to be completed faster, allow you to make more confident decisions. Kind of whatever bends come down the road for you and your project, you'll be able to handle them with expert level advice and experience from many projects from yours truly. So let me follow the links there and book a discovery call if that applies to your project. Thank you for watching, and I will see you tomorrow on The Shock Show.